Okay, we will go ahead and get started here. My name is Aaron Magnan, and along with me I have Tony Holtz. He'll be introducing himself in just a moment. But today's webinar is all about how you can accelerate your design validation using Fusion 360 in combination with a company called Protolabs. And I'm really excited to be doing this presentation, and I'm expecting to learn as much as everyone out there. Real quick about me, I'm a mechanical engineer. I went to the University of Nevada, Reno. I have a lot of background in simulation products, and I'm a technical marketing manager over here at Autodesk. Along with me is Tony Holtz, and I'll let Tony go ahead and introduce himself. Tony, you there?
Yep, I'm here. Thank you, Aaron. Yes, I'm Tony Holtz. I'm currently the technical specialist here at Protolabs. Working with the marketing group. Now, my background here with Protolabs, I have about 14 years of experience growing up with the company. I'm very familiar with the CNC machining process, our mold build process. I have been the lead mold designer within Protolabs, as well as kind of guiding our quoting team. So the information that we're going to be presenting to you on trying to manufacture a part through a design analysis is something that I work closely with those groups, and as well as being a lead applications engineer for a handful of those years also. So now I'm doing presentations here like we are with Aaron, trying to educate our customer base on how rapid manufacturing at Protolabs can be used. Next slide, Aaron. So, exactly who is Protolabs, for those of you that aren't familiar with us. We have three technologies for rapid manufacturing. One of those technologies is 3D printing. It's very popular out there right now in the industry, and there's still a lot of unknowns. We have three technologies currently here. One is stereolithography, one is selective laser sintering, the third is direct metal laser sintering. Well, you might need a little bit of improved material characteristics or difference in, capabilities. We do offer CNC machining of over 30 thermoplastic materials, metals, soft and hard materials for milled components and for turned components. So we do offer lathe with live tooling for our metal components as well. And then what we're going to be focusing on today is going to be the injection molding side of things for your commonly used thermoplastic injection molded components and your thermal sets, your liquid silicone rubbers. Next slide, Aaron. Yes, continuing on a little bit of who Protolabs is. Protolabs really excels at speeding up your time to market. So traditionally looking at maybe a injection mold that was maybe produced 15 years ago or still today in a production type setting for an injection mold, that's going to take well over 4 to 12 weeks to get manufactured and parts delivered. What Protolabs does is it really breaks those boundaries and utilizes 3D CAD software from building it from your 3D CAD that was built and taking that, integrating it into Protolabs software, generating code that can give immediate feedback for design analysis and provides code for a CNC machine. Really automates that process. So we're able to turn around a real injection molded part as little as one business day. So we really can turn around injection molded parts overnight, depending on size and complexity. Now the standard lead times can be right around 15 business days, but absolutely can expedite near all components much faster than that.
Well, thank you so much, Tony, for telling us about Protolabs and the technologies that you have under your umbrella and have at your disposal. Like I said, I'm learning things about Protolabs already, so thanks for being a part of this. Real quick about Fusion 360, I imagine a lot of you are here. Maybe you found out about this webinar from our website, but Fusion 360 is a 3D CAD, CAM, and CAE tool. So if you want to design something, you want to produce it, you want to test it, you want to do some analysis on it, it is going to do all of those things for you. It works on both Macs and PCs. I was joking with Tony about this earlier. I'm working on a Mac today, but I imagine he's on a PC due to limitations of other 3D design softwares. You can get into the industrial design aspects using our Sculpt and T-spline technology. You can get into your mechanical and parametric designs. You can do renderings. As mentioned before, we have some finite element analysis already there, and there's some big stuff coming in the near future, and same goes for CAM. And I think one of the major benefits of Fusion 360 is its ease to collaborate and work across teams. I mean, because your data is stored on the cloud, it's so easy to share for anyone to access from really anywhere with various devices and operating systems. So really easy to work with. Me and Tony were collaborating on this project, and you can see what we're going to be building is this example part. I think it lends itself to some issues that you'd like to avoid when you're designing plastic parts that are intended to be injection molded. I mean, for those of you who are not familiar with injection molding, I mean it's a very common process for plastic parts. It's very prevalent in industry. You can produce a lot of parts at a low cost, but the big upfront cost is the tooling that Protolabs will help you produce. So this is the model we're going to be building. Before I get into it too far, I did want to point out that in addition to all that Protolabs has to offer from the technical standpoint, they also have a lot of guide for your different design. So I actually wanted to bring up this design for moldability PDF that they put together. I mean, this injection molding process is something that requires some background information. What Protolabs does is makes it much easier for someone who's new to this process to get to production that much faster. But if you want to learn more about this and learn about what to avoid, I'd really recommend that you take a look at this guide. I'm just kind of scrolling through it very quickly. And then I'm going to show you some design actually in Fusion 360 as the next step. So I think, like I say, this presentation isn't all about Fusion and how to design in Fusion. It's really about how you can use Protolabs to leverage what you create in Fusion. So at this point, if I wanted to get a mold made for this, or to learn about, if it's designed properly and if it's going to adhere to all those rules that are very important for your plastic parts, at this point I just use the drop down under Make. And I'm going to use my Protolabs link that you see here. I'll select the component right from the graphics area. So if you have 20 different components in this in an assembly design and you just want to get one made with an injection mold, you can select a specific one at that point. I'll click continue, and then it's going to start to upload this to Protolabs. So it's actually already attaching the file for me. All I need to do is type in my email address, select the process that I want. So in this case, I'm looking to get some plastic injection molding tooling made. I click continue. This is related to, Tony could probably tell you more about this, but just depending on who they're actually dealing with at this time. Once I hit submit, it's going to go to Protolabs, and literally in 24 hours, I just did this yesterday for another project I'm working on. You get a quote, and you get a lot of details pertaining to the design that you're making and its moldability. So I think that's all I had to cover. Tony, are you ready to go?
Yeah, absolutely. Yeah, that was very interesting, Aaron. Well, perfect. Well, it's a nice thing between Fusion 360 and Protolabs is that Protolabs does not want to be the parts designer. You have full control over your part design. So everything Aaron was doing on there, he's assuming what draft might need to be applied on the parts. And customers do that for us right now. They'll send us a CAD file with draft on there. They CAD file without draft. So as Aaron mentioned as well as how quickly these quotes come back, I think it was more of a design for manufacturing, not a quote, that we try to get these back in 1 to 4 hours. So if you have a very simple, non-complex design, you can expect that near instantaneously in some cases. Some parts that are much larger, they have a lot of bases, that might take our computers a little bit longer to compute those. So we have developed internal software here that can take your Fusion 360 CAD model and break that into a million computer points, analyze those individual points, and then compile them back together, and then automatically send you these quotations. It's very hands-off as far as who's looking at these. Nearly all of our quotes go out that way, but some of them need a little bit more hand-holding. We actually have some analysis people here that actually go through and review those parts. What you get in return, once you've uploaded that CAD model for injection molding, is a email link that will bring you back up to this screen right here that actually is going to have, who is the quote designed for, the name of the part, the dimensions that you might want to be looking at, and a visual of the part. So Zarin said that, there's some color coding that you can put on there for a different draft analysis. Our software looks at side assignment. So in that image, you can see that there's some green faces, blue and pink. Those are referencing the cavity side or the A side of the tool. The core side or the blue side is the B coloring. And then any other additional colors are going to be any side actions or hand-load inserts that are on there. The only section that's really a quote is going to be this confirm or modify pricing. So this is fully interactive. You have the abilities to select a single cavity mold, which is generally what I guide people or instruct people to build on, because it's very low cost, it's less risk than jumping right over to a multi-cavity tool. You would have the ability, based on geometry and size, to go up to a 2, 4, or even 8 cavity mold. This particular part design, as I say, it might be a poor design part. It has a couple side actions on here. So that's why you might see a little bit of a higher pricing on here. But the tooling is actually going to begin at about $1,500 for something small in your hand. Size and complexity is going to start to bring that part up. This part's fairly tall, fairly wide. As a side action on this, you can see the price is going to start to increase a little bit. You have the ability to adjust different surface finishes based on Protolabs capabilities, not Moldtech finishes, because these are aluminum tools that are CNC machined, so we're hand polishing these. We can even apply grit blast to apply a light or medium bead blast finish. And as you change these, the pricing structure will automatically be adjusted for those finishes. Same with your initial sample quantity, anywhere from 25 up to maybe 500 quantities. You can see your piece part price is adjusted, or your total price is adjusted. Again, it's a very poorly designed part. It's fairly thick right now, not a whole lot of coring, so there's a lot of part volume on here. Most part costs right around $2 per part, depending on the material that is selected. You're going to have a few hundred different materials. These are actually the most commonly used resins for Protolabs. And then we have the ability to run secondary materials, change colors for any material. These are just a handful of colors that has been run with these specific resins. We can also run customer supplied if that's what you need. When should you expect parts? Based on, again, size, complexity, we're looking at your part, how fast we can get that manufactured. 15 business days is going to be the standard price or the standard delivery time. But based on the size and complexity, we're going to allow an expedite to 12 days, 10 days, maybe even up to that 1 business day turn for the injection molded part. And then it also actually shows what the specific expedite fees may be for your particular part geometry. Are you interested in maybe production components after the initial prototypes are done? Well, you can already get some pricing structure already done in here. Per order, maybe you need 10,000 parts or 100,000 parts. You simply would then, type in how many quantity that you need, click go, and it's going to calculate the large volume orders for you. Let me get down here. This is kind of where the most important areas are on here. This is actually the design analysis. So the second view on here, manufacturing analysis here, this is what I would recommend all users. You get your first initial design done, submit it to Protolabs. You saw how easy it was for Aaron to upload the CAD model. So whether it's you're going to lunchtime, you're going home for the evening, submit your CAD model. You come back in the morning, more than likely, you're going to have this analysis here. Now you can go back and actually apply those draft angles or apply radii, start coring out some part geometry to actually make it more manufacturable. I don't like this strobing effect, so you can quick highlight those issues off and actually like to adjust that transparency so it's a little bit more solid. Again, blue is the core side. Usually the side where ejector pins are going to be located. Greens usually are more cosmetic outside facing the surface of the part. Now that you have an understanding of how we're envisioning the part to be molded and the mold to be designed, you can better design your part. Well, things to look at here is there's going to be required changes in the first half of the second section. Based on the depth or manufacturing capabilities for CNC machining these tools, we might need either a half-degree draft, 1-degree draft, 2 degrees draft. And based on the depth of this feature right now, we're actually going to be asking for 2 degrees draft clearance. You may have applied a draft already to your part, but it might not be great enough for us. A very good rule of thumb for applying draft to your CAD models is look at maybe about a 1 degree of draft per inch of cavity depth. That's just a rule of thumb, but it gives you a nice starting point because all injection molded parts require draft angles on them. You can spin the part around. You can look at different draft features. If we need a different draft requirement, it's going to be up in another section here, so number 2. Now for these little feet on here, it's much shallower. We have more accessibility with some tooling. So now we can apply a half-degree of draft. We don't need a full 2 degrees of draft. But if you want to give us more draft, by all means, please do if you're trying to keep more consistent draft on your entire part. A few things that not all CAD softwares actually pick up on, maybe some thin areas. So right on this feet, you have these couple teeth on here, and these are actually going to be aluminum blades that come in creating or separating these teeth on here. So it gets a little thin. We generally like to see at least 40 thousandths or 1 millimeter for any aluminum blade, but that can be dependent on draft and height of these features. If you want to double check against your CAD models, move your cursor to a specific location and type the letter D. You can see that there's actually a graph or a chart that pulled up here measured in X, Y, Z, even X, Y, and X, Y, Z. So you kind of rotate the part, move your cursor to the other side. You can see that we're sitting right around about 0.3 millimeters. So it's a little thin. So we're going to actually ask for something to be a little bit wider, closer to 1 millimeters for that. Hit the letter D, that goes away again. Shut-off clearance? Shut-off clearance is, 2 halves of the mold that are actually sliding on one another. Aaron had this little cut in here with this little hook or little feature on here. There's no draft on the sidewall of this part. So the draft can be applied to the sidewall here at 3 degrees draft. That would give us the proper mold clearance for these 2 pieces to actually slide on one another. Another way to actually do that would actually be kind of cut and core this piece out a lot more. And then the core that actually extends through this would actually have an angle that kind of built on that. Any undercut features, very easy to design in some undercuts. In this case, the actual radii that was actually put on that same hook feature can even kind of wrap down and create a knife blade edge as the shutoff is produced. So in this case, we're actually asking you to remove radii when you might think radii is, nice to actually have in your molded components. Another area where Aaron was trying to core out the part a little bit, kind of get rid of some of that thickness, that mass, something that usually isn't achievable for light in injection molding. Our software actually picks up these thin areas based on a percentage of the nominal wall thickness. What what can happen in these thin areas if it's too thin? Well, as plastic fills in through your mold or through the part, it actually flows in a path of least resistance. That means it's going to flow through the thicker areas first, backfilling these thin areas. You're able to pour knit lines, or even worse, it's full in your part. So our software tries to allow you the best possible outcome for your injection molded components. The same thing goes for the thick areas. Now, although you try to core out the top of the part through this ribbing, but these feet are still very thick. Now, we try to, again, based on percentage, not looking at material selections, that can play another factor into this. You might have some porosity, you might have some sink. So you might actually want to try to core out your part the best way that we have shown here. But now you have to be careful coming in between these little fingers here. That's going to create a very thin blade again. That might infringe on the thickness that we need for our tools themselves. Minimum thickness is another thing that we actually call out on here. So this is going to be different than actually thickness required for molding your component. This is strictly for manufacturing. Based on tooling diameters, CNC and mills, we have guidelines on what thicknesses are required for these tools. Now this can vary anywhere from 26 thousandths of an inch to 0.66 millimeters that's shown in here, 35 thousandths of an inch, maybe 51 thousandths of an inch. So it all depends on the cavity feature or the feature depth of each component and the draft angle. They play or they work well with one another. So if you need to have more draft or less draft on your part, you might have to go thicker with the wall section or vice versa. We also show some different moldability advisories. So I mentioned that draft is required for all molded components, but based on manufacturing alone, we can manufacture some features at zero draft. So you can leave the zero draft in there, but we'd advise you that we have at least a half degree's draft clearance on any feature that's going to be molded. A few different things that we can actually show in the CAD analysis or the design analysis here is actually gate locations, ranging from a hot dip or a direct gate here in this case, tab gates, even pin gates are possible, and a flow analysis tool. So the flow analysis tool is nice to actually request so you can actually see maybe where potential knit lines are going to be located or potential shorting. So remember those thin areas that I mentioned before? The flow analysis is actually going to confirm that based on the flow properties of, in this case, ABS polycarbonate. So the green fills your cavity. You can see this gray hollow void here. It's going to compress and trap all of that air in there so that you won't get a full completed part. So this is something that does oftentimes show up in your quotes, but if you do not see it, you can request it. We'll simply add it to that. The other information, the third section on here, actually shows some different radii images and how the tools can be built. You don't need to go back and try to model in this varying radii here. You can simply choose the largest radii or leave it square. This is just showing you an example of what to expect when your part arrives. I mentioned complexities. Complexity as far as side actions. So if you want to try to decrease the tooling costs, you can eliminate some of the features that require side action, as complexity relates itself to cost. You can get a summary of everything that you have just done selected on the top section in one. You can upload a revised model directly from here if you already have a revised revision, or you can simply upload the new CAD model right from Fusion 360 again. What Protolabs does offer is if you have some very simple changes that are needed to be made, Protolabs might go and actually tweak your CAD model, and you can actually view the proposed revision that we offered you. You can download that CAD, import it into Fusion 360, kind of see how that makes together in your assemblies, accept it, or make those changes and resubmit it for another quotation again. Tolerancing is stated listed down here in the note section. So based on material selection, the tolerance may vary and change depending on what material criteria you select. If you have any other further questions, right from the quote, you can click on the Protolabs signal up here. It actually brings it to our actual web page. You can get another quote, or you can kind of check on different guidelines and things like that. For plastic injection molding, what type of sizes can you do? Some other different design tips. We talk about different draft angles here. Part sizes, nearly 19 inches by nearly 30 inches. You can get a real injection molded part in 15 business days or less. We have the different fundamentals of molding available here. It kind of talks about different things that would help guide you along with your CAD designs, with additional different resources, whether they're white papers like Aaron showed you. You can request different design aids, view what different materials there are here. So, Aaron, anything else that kind of caught your interest? You want me to elaborate a little bit more, or I can hand it back over to you here?
Well, thank you so much, Tony. That was a great rundown on what to expect from the Protolabs quote. You offer other services as well. You right from the drop down from the quote process that we go to, you can also get plastic parts made, right? As in
Yes,
printed parts. Sorry.
Yep. So in looking at the webpage here again, CNC machine parts, in 1 to 3 business days, typically the 3D printing components, dimensions, stereophotography, selective laser sintering, direct metal laser sintering, good for quantities of 1 to 50 components. Generally speaking, 1 to 3, 1 to 5 days. The 3D printing of metal can sometimes take a little bit longer. That's why we kind of state this at 7 days. Now, as long as you have an STL file format, you can get instant quotes right online for 3D printed components.
Well, I really, really appreciate you going through that. I think that just about does it for the webinar. Make sure to take a look at what Protolabs has to offer. Take advantage of their expertise. I mean, Tony obviously knows this industry inside and out. Thank you all for attending. I hope everyone learned something. I certainly did.